All right, so last time what we did was we looked at how we actually created voltage. Again, voltage is going to be that separation in charge, and the separation is going to come at that cell membrane level. Right? We had the positive ions on the outside of the cell membrane, negative ions on the inside of that cell membrane. So now what we need is current, which is going to be the flow of these ions, or the movement of these ions, and they're going to move across the cell membrane, and that's going to create an electrical signal that will travel down the length of the axon. And that's really what we're trying to get at. Okay, so first let's separate them, and now we got to get them to move in a very precise sort of way, and then it's gonna travel down the length of that axon. Okay, so let's talk about that. How does that? All right, so let's see if I can get my pen here. All right, so here's our cell membrane. All right, and let's just kind of remind ourselves this is outside the cell. This is inside the cell, right? And color. All right. So again, what we saw, and let me just kind of back up here. What we saw is outside the cell we have lots of sodium, right? And then inside the cell we have lots of potassium, right? And we had mentioned last time, here's our graph, and I apologize for the kind of wavy lines, but I can't draw straight lines with this thing. So here we are at 0 millivolts. Down here we are at negative 70 millivolts, 70. And as we had mentioned, this the voltage, if we put a little electrode into the cell membrane, it would read at negative 70 millivolts, right? That's when this axon is at rest. All right. So now what's going to happen is we're going to talk about some different channels. Okay. So the first channel we're going to talk about is something called a voltage gated. So this guy right here. This is a voltage gated sodium channel. Now this is going to be different than that leakage channel we saw in the previous video. So what's going to happen with this is that when a certain voltage is reached, this is going to open up. Otherwise, there's a gate on it. Okay. So again, when a certain voltage is reached, this is going to open up. And basically, as soon as it opens up, all this sodium is going to come flooding, and I mean flooding right inside that cell. Right? So what's going to happen, if you kind of look up here in the upper left, your cell's going to be chugging along at that negative 70 millivolts. Some sort of stimulus is going to come in. Now, the exact kind of stimulus is going to depend on where we are, because obviously nerves in our eyes are reacting to something very different than nerves in our ears, which is very different than touch receptors in our fingers and our skin. Okay, so just whatever a stimulus comes in. Okay, and what it's going to do is it's going to take us from this negative 70 millivolts, and it's going to basically trigger some of these ion channels to open. Right? Not a lot, and and it's kind of interesting. They don't wide open. They kind of like slowly open. So as you can imagine, as you're slowly opening something, more and more trickles out, trickles out, trickles out until it opens up totally, and then you get a flood. Okay. In any case, so you have some sort of stimulus come in. The membrane potential the voltage is going to change to become more positive as some sodium starts leaking in. But once it hits what's known as a threshold, right? So once threshold is reached, and threshold, in the case of most of our neurons, is going to be negative 55 millivolts. So once we hit this negative 55 millivolts, once threshold is reached, the voltage gated sodium channels open completely. Okay, so these voltage gated sodium channels, they open, sodium is going to come flooding into this cell. Okay, does that make sense, hopefully? So again, we have some stimulus come in, these channels are going to open little, it hits this threshold, boom, They're blown open. So now all of a sudden, all this positive charge is coming into the cell. So we're going to see, if we're looking at a graph, is that we go from this negative 55 millivolts, and we're going to quickly rise up into the positive range. Okay, and what's going to happen is we're actually going to reach up to positive 30 millivolts. Okay, so hopefully that makes sense. So once threshold is reached, so once negative 55 millivolts is reached by whatever that stimulus is, the voltage gated sodium channels open completely, right? So this is sort of step one. Step two is that sodium, that's a plus, sodium rushes into the cell. Okay, so I'm going to rush into the cell, right? Which causes the cell membrane to depolarize. And what we mean by that is it becomes more positive, right? So again, rest, rest, rest. Some sort of stimulus comes in. We hit that negative 55 millivolts. Sodium channels open up. All the sodium comes flooding into the cell. We go into the positive numbers, right? So we have a positive voltage now. Okay. Again, because these are voltage-gated ion channels, so I'm sorry, I'm kind of writing all over the place. I'm going to hide me if I can. Let's see. Hide me. So the third thing that's going to happen, right? So sodium comes rushing into cell. It causes cell to depolarize. Once the membrane potential reaches positive 30 millivolts, the sodium channels close. Okay, does that hopefully make sense? So again, these are voltage-gated channels. That means that depending on the voltage, they'll either open or close. So at negative 70 millivolts, they are closed. Some stimulus comes in, it kind of causes them to crack open. A little bit of sodium comes in until we finally reach that threshold, which is negative 55 millivolts, at which point the voltage channel is completely open, which then causes sodium to come rushing into the cell, causing the cell membrane to depolarize, right? So it becomes more positive, and once that membrane potential reaches that positive 30 millivolts, again, the sodium channels close. So they're closed at negative 70 and at positive 30, they're closed. Okay, and in between there, sodium's coming into the neuron. All right, so sorry to I'm sure as you're watching this, it looks like a big jump. I had to clear the screen, and I don't have an eraser on this. So I cleared the screen, and I redrew the cell membrane here. So it's cleared everything away. Here's our little graph that we looked at before. So again, cell was chugging along. Something caused it to depolarize, hit that threshold of negative 55 millivolts rather. At that point, the sodium channels opened up. We hit positive 30 millivolts, sodium channels closed. So now, no sodium is coming into the cell. Okay? All right. But what goes up must come down, right? So let's take a look. We have another ion channel we haven't talked about yet. Let's see what's a good color. Maybe blue. All right, so we have another channel. It also has a voltage gate on it. Okay, these are called, let's see, voltage gated potassium channel. That's okay, potassium channel. All right, so these voltage gated potassium channels are closed until, so let's see, the voltage gated potassium channels are closed until the membrane potential reaches positive 30 millivolts. Okay, so at positive 30 millivolts, oops, say positive 30 millivolts, the voltage gated potassium channels open. Can you guess which way the potassium is going to go? Remember, it was really highly concentrated inside the cell, so if we give it away, it's going to want to leave, right? So potassium floods out of the cell. All right. So now what ends up happening, so if we look up here, so up here in the left-hand corner, so we had, again, we were going along, some stimulus came in, it opened up those sodium channels, right? And at positive 30, they closed again. But now it opened up potassium channels, and now potassium is flooding out of the cell. So as the cell is losing a positive charge, the resting membrane potential goes back down negative. Okay? So we've lost a positive charge, so it becomes negative. All right? So what that is called, so this process of it going more negative, this is called repolarization. So we say the cell repolarizes. All right? And then what's going to happen is the sodium-potassium pump that I mentioned way back when is going to then kick in, and it's going to pump everything back to where it should be. So it'll pump the sodium's back out and the potassium's back in. And it reestablishes the gradients. Hopefully that makes sense. Let's take a look at some pictures. Hold on. Okay, so here's that image I was mentioning to you before. Here's that resting membrane potential. So again, if we take a look at the cell membrane on an axon, so here's our phospholipid bilayer. So here's our resting membrane potential. Again, positive charges. Oops, sorry about that. Positive charges lining up outside the cell, negative charges lining up inside the cell. Okay, and we can actually record this, and people do. Right. We have something, what we had talked about, that stimulus coming in was a graded potential. So basically what that meant was some stimulus coming in, it's changing that membrane potential from that negative 70, and hopefully once it gets up to that negative 55 millivolts, again, those sodium channels are going to open. So we call that depolarization. However, something key, sometimes the stimulus coming in can be small enough that it doesn't quite hit negative 55 millivolts. It may only hit, let's say, negative 60 millivolts, so it doesn't quite hit threshold. If it does not hit threshold, you will not get that signal to go down the length of the axon. It doesn't go anywhere. It's not enough. It's not strong enough. You have to have those sodium channels open up wide. Okay. So again, that's depolarization. So it's depolarizing. And once we actually get it to that threshold, we call that an action potential. So again, once we have an action potential, that's the signal that's going to travel over the surface of the cell without dying out. And the phrase for that, the traveling over the surface without dying out, is called propagation. We say the signal is propagated down the length of the axon. All right. And I do have another term here, something called hyperpolarization. Ever so often, the signal that you're getting, the stimulus coming in, doesn't cause depolarization, doesn't cause it to go more positive, like from negative 70 to negative 55. Rather, that signal actually makes the neuron go from negative 70 to more negative. It's like a negative 90, which means that it's just that much more difficult to get that nerve to fire. Ever so often, you're trying to inhibit your cells. You don't always want them firing. It's just like a car. We all love the accelerator. We need to hit the gas pedal to go, but as we all know, we also have to be able to stop. There are some certain situations where you have to hit the brakes because you don't actually want to go anywhere. Okay. So similarly, neurons are going to have the brake, and they're going to be able to hyperpolarize, and that's essentially sort of like the brakes. It's that much more difficult to get them to go after they're hyperpolarized. Right. So here's just another a better graph than the ones that I was drawing, and hopefully this will make a lot of sense to you. So again, the changes to our resting membrane potential that leads us to that action potential. It's that signal propagating down the length of the axon. You can kind of see this here. So let's just take a look at this graph and the color-coded regions. So here in this purple area, we said the resting membrane potential is at -70, right? The voltage-gated sodium channels are in a resting state, right? And then the potassium channels are closed. So basically, the sodium channels are resting. Then they call it resting versus totally closed because, as we had mentioned, they can kind of crack open a little bit with that incoming stimulus until they open up wide. Okay. However, these potassium channels, basically they're open or they're closed. So there is no kind of cracking them open. Anyway, so here we have, again, the signal kind of resting, -70. And then here at the start of this blue, some sort of stimulus comes in. Again, whatever that may be, just depends on where you are. It's going to cause the membrane to start depolarizing. And then basically, once we hit that -55 millivolts, those voltage-gated sodium channels are going to open. Choom! Lots of sodium comes rushing into the cell. We go to +30 millivolts. Okay. At that point, the sodium channels are going to close, and the potassium channels are going to open. So we're repolarizing. Okay. So basically, here we are repolarizing, and you do have a hyperpolarization phase because these potassium channels, it takes them a little bit longer to shut. So they're getting the signal to shut. They've hit that threshold. They're being told to shut. However, it's just taking them a while to close. So you go a little hyperpolar until that sodium-potassium pump basically puts you back to your resting membrane potential. Okay? Hopefully that makes sense to you. A couple of other terms I just want to bring to your attention is this idea of an absolute refractory period and then a relative refractory period. Now, during the absolute refractory period, basically you cannot, no matter how much you want, get another action potential to go. Okay, you simply cannot. Basically, if you take a look at this absolute refractory period, these sodium channels are either open. You can't open something that's already open. Like I can't turn on the lights if the lights are already on. I have to turn them off before I can turn them back on again. Hopefully that makes sense. So you can't get another action potential to go. It is signaling. The lights are on. I can't on the lights any more than on. And then here, they are basically inactivated. So they have to be reset before they can open back up again. Okay, so it's an absolute refractory. It cannot, no matter how much you want, elicit another action potential during this time period. Now, in a relative refractory period, down in here, the sodium channels are in the resting state, but what's going on is the potassium channels are still open. So now I can get another action potential to occur at this point, because again, the sodium channels are ready to open up again for me. However, we're still losing a positive charge. So we can, however, it's going to take a much stronger stimulus to get a second action potential to go anywhere in this, I don't know, orangish bar area. I kind of think of it this way. It's kind of like trying to run up an escalator that's going down. Yeah, you can go up the down escalator. It's just going to take a lot more work, right? Because you're fighting the flow of ions, or the flow of the stairs, if you will. All right, so I'm going to stop this video right here. I know this can be a lot, so please let me know if you have any questions on this. It's really an important concept for us to understand how these electrical signals are transmitted. It's important in our health and our well-being, and it also allows you to understand like how different neuropathies occur. So if you have any questions, always feel free to email me, and I will try to clarify any point. Okay? Till then, see you later.